For first part of today's session, I will tell you more details about software design and mostly about some important approaches how you design your software to do several things. And in this part I will cover most important topics about object-oriented design, and these topics will be coupling, cohesion, abstraction and composition, and also I will touch some of software design patterns, not all of possible ones, but these ones which are usually needed to create some kind of standard software which is not too simple and not too complicated. And of course all complexity comes from many easy things put together. And before we go into patterns, some of you already probably know it, but you may design software in different ways. You may start designing it bottom up, that means from small simple things which you then build together, or you start with top-down design with large and abstract things and maybe complicated things. Do you know precise difference between complicated and complex? So either this or that. And then you split it apart and you go into smaller details which are simpler but more, and you somehow put them together. And neither of these approaches is ideal. As usual, in real life, in real engineering, nothing is ideal, only models can be ideal, like ideally black body or ideally white body or ideal conductor, but in real life there are benefits and drawbacks. And usually what happens is, if you start designing your software from scratch, or you never do it from scratch in modern days, but let's say with very generic, very general software and things, then you usually start with top-down design, because first you need to understand what your general vision is about this software, and then you, according to this general vector where you are heading, where you are going, you fill more specific details how it should be designed, implemented, how it should work. And therefore, for such kind of software, you usually start with very general and abstract and complicated things, and then you go deeper until everything is more or less understood, at least according to current state of knowledge of your project about this software. And you create as many parts as they are needed, but not more, because otherwise you are risking make unneeded complexity of your software. And when you split everything in parts, splitting is tricky, because you may split your designed software in useful parts or not so useful parts. And for example, if you learn something about anatomy of body, usually you just don't split it on vertical axis in two halves and then talk about the left half and right half, because even though there is some things you can learn about symmetry and asymmetry in body. This is not a good approach how to analyze body. So you think about functionality of body, about limbs and about digestive system, etc. And similarly for software, when you split it in parts, you should think about functionality and to make good borders between these parts. And what are these good borders? Good borders are, if you apply general thing, is that first there is minimal dependencies between these parts. There are always some dependencies if they are related, but you minimize these dependencies. And specific term for this is called coupling in object-oriented approach, which means that something is coupled together, like chained together with heavy dependencies. And the worst possible thing is hard to see coupling or hard to see links between these things because of poor designs, that everything is not visible easily. So that's one thing. Another thing is that to minimize these unneeded dependencies, and in concrete specific terms, these couplings, these calls from function to function or method to method, transferred objects or structured data types from method to method, etc. You maximize cohesion in such a way that similar things are put together and different things are put apart. What are similarities? Similarities are similar data structures and similar behavior. And here inheritance and polymorphism comes in, so you can make more general abstractions like general abstract classes about quite similar but little bit different objects. And then there's also important thing to see difference between containers and between essential parts of something. So that's about aggregation and encapsulation. And these are two metrics what you can apply to think about your design. And important thing is that even with poor design, you can implement software which will behave correctly. Only thing is that you will lose time to implement it, time to test it, time to maintain it, etc. Because if design is not optimal, then your work is less efficient, so you can't do as much as possible with a more proper approach. And therefore, in tricky cases, there is no simple distinction between similar but different designs in terms of their usefulness and quality, because in real life nothing is ideal, and there are of course many approaches for very insane and wrong design, but in any more complicated situation there is no clear winner how exactly you design your software. So about coupling, what I can tell in more details, particularly for software, coupling means calls to methods, transferred objects to methods, and the worst possible coupling are unintended side effects. When you call some method, some property of object is changed and it is not easily caught or noticed that something changes. So methods never should do any side effects or change something which is not clearly visible from the naming, from overall design. And that's about coupling. And for cohesion, so important thing is to see differences and similarities between your entities or these business objects, and you should understand what is generalization of something and what is part of something. For example, you can't say that acorn is an oak, because oak is completely different entity or object than acorn, like ozols, nozels in Latvian. But there are dependencies, and if these dependencies are fulfilled, acorn may become oak, but then of course it has become something completely different. But the branches may be parts of oak, and again, or tree, and branches are not tree. Branches are just parts of tree. But if you look on similarities between objects, then you can see that there are different kind of trees, and if you can say that tree is actually generalization of many different species of trees. So that is similarity between this tree and that tree, and so in such a way you introduce inheritance, or you describe something with some more general thing. And inheritance means that you introduce some generalization between different but similar entities or business objects. And if you work in business process automation, everything what is known probably is class. And then there may be different kind of classes, like if you look on different kind of documents or papers, electronical or on paper, again you can see that there is some generalization like document, but document might be printed on paper, or it may live only in electronical form. So then document is more general parent class for these two different kind of documents, either in electronical form or in paper form. Both are documents, but there are small differences, and that is an important aspect to design proper software, because with such an abstraction you can introduce similar handling of different items, and in many cases these differences actually doesn't matter. For example, you may create some automated process where both written papers and electronical papers are handled in the same way. For example, usually you create so-called adapter that you scan your paper into electronical form, and then you deal with paper documents in the same way as in electronical documents. And here are concrete examples that without inheritance you have duplicated data structures, and that means your design of system is not lean enough and simple enough. But if you say that, for example, manager is just one specific set of employees on your system, then you can just add missing things for manager what you do not have in employee. So this is class diagram, and this is probably Java code or Kotlin code or whatever. And then what is quite important is that in proper object-oriented approach, when you use inheritance, you add complexity. For example, in Java, most simple data structure is called class object, which doesn't have anything inside it, but there are some rudiments to deal with multi-threaded programming, access blocking for it, etc. And then actually class employee extends object and class manager extends employee, which extends object. So remember that if you use inheritance properly, these more specific classes add some complexity, either in data structures or in behavior, what like methods do they have. If you need to hide complexity, there may be some exclusions in any rule, but this shouldn't be general approach. And then you can use this polymorphism principle that in many cases, if you don't care about managers, you care only about employees, you can handle all these data, all these entities in the same way. So you don't need to write additional code, make a specific design in your system to deal with these small differences. And then, when you need to add complexity, sometimes you need to override or re-implement or rewrite some methods in more specific cases. And again, here, with proper design, you need to add complexity. For example, if there is method which shows you details about your employee object, and by object I mean it is jargon, it should be properly called instance of an employee class. But in usual cases, nobody says it in such ceremonial way. They say that instance of a class is an object, and in most of cases it doesn't add confusion, except when you talk about Java object class, for example. And then again you may add some complexity that you rely on already implemented thing, how you deal with standard employee, but then you say that if it's manager, then you do something more. And composition is, and by the way, in general English, when you say that something extends this, in basic English it's called that manager is an employee is an object, and so it's something like fulfilling more general roles. But composition is different thing, and it shows internal different parts which are put together to make more complicated thing. For example, a body can consist of limbs and body itself and head or whatever, or car has an engine, body and 4 wheels, or truck has an engine, frame and 10 wheels. So, and these are completely different ones. There is a big difference between engine and body and wheels, but these many different things put together makes some more complicated thing. And in general English, composition is called has a, and some parts here. And if you are still confused about inheritance and composition, here is example from real life and example in object-oriented approach. So here is class diagram in UML. Here is excerpt of code, and here is real machine. For example, you have Coke machine, which allows you to get Coke and orange juice dispensed or get out of it. Then if you use inheritance, you inherit everything from this previous object, but you add some complexity, and for example you also create output which creates cocktail from Coke and orange juice. And this is proper inheritance because you add complexity, you do not hide complexity in your more advanced thing. But if you use composition, you can create something completely new, and in this case the completely new is absolutely different box. And inside this box you create output which makes cocktail from Coke and orange juice, and then for some reasons, this is again about other design aspects like security, you may encapsulate this internal object, this machine, that it's actually not visible from outside, and everybody thinks that there is just yet another different object which provides you cocktail from Coke and orange juice. And in UML class diagram, this means that the Coke orange machine extends drink machine, and here are not shown details about these outputs. That would be some kind of either attribute or method, probably method because it behaves. Or here you say that the drink machine is essential part, encapsulated and hidden in this case, inside this Coke orange machine. So encapsulation you use quite often because if somebody can access your data structures and methods, how to deal with them, they also may abuse them, either unintentionally or intentionally. And therefore, if they cannot access these data structures or these methods, they cannot abuse them and break them. And therefore, for any system which can be accessible through the internet, you need to deal with encapsulation and security, or limiting access to internal parts of your system quite seriously, otherwise it will be very unsecure and probably will be broken. So if you could see this Coke and orange machine and could access it as well, then it would not be encapsulated. It would be just a visible part of this Coke orange machine. But if it is encapsulated, actually nobody can see what is inside. What they see is only this particular feature. And if you look on programming language, why encapsulation is needed, because if you rely on more general behavior and data structures, they may not have limits what you need for your business cases. For example, if you create class myDate, which has 3 integers inside it, then probably you do not have any meaning for negative numbers for months and days. You may introduce it such arithmetic that the negatives goes from 0 back like for years, but in many cases you need to add some limits that, because there is no specific type which allows you to hold for values from 1 till to 31. You use these more generic or more general data types, and then you make them encapsulated or private in most of programming languages, and you allow access to them only through available methods which deals with these ranges and checks for quality. And then you may introduce also abstract classes, and abstract classes are classes which do not have instances or objects in jargon. Why do you introduce such? Because you can put their internal data structures and behavior as a holder to house these definitions there, but when actual instances are created, then they need to have more specific classes, so there shouldn't be any object with type vehicle in this system, only truck or river barge. I'm not sure that your design will need like abstract classes, but it may be. For example, typical case is you need to have interface with different service providers which are very similar by their nature, by their business objective, but are very different in technical details. Another typical case is if you want to implement different kind of encryption algorithms because their business case is very simple. They need to encrypt and decrypt data, but the concrete algorithms are completely different, and therefore again you use some abstraction where you just say something like encrypt, decrypt, but specific details are of course depends on specific encryption, decryption algorithms used. And then there are interfaces which, from UML perspective, from modeling and design perspective, are specific abstract classes. Interfaces are public abstract classes, and their role is that because these are public and these are abstract, they are used as a boundaries between one part of system and another part of system, and because these are public, you can see that part of system and access it. And in real life world, interfaces are different kind of connectors, like plugs and sockets for electricity, for data transmission, for coupling trains and coupling trolleys, etc., etc. And then what is important is that depending on how exactly this interface is implemented, with this more abstract class, you can use this polymorphism that there may be many different objects which from general perspective, from interface perspective, allows you to fly, but actual approach, how exactly they fly, are very different. And important part about interfaces are that these are public, and if you have too many interfaces in your system, then you may violate principles of encapsulation or hiding your internal complexity of system, because any interface is publicly available and anybody can try to use it. So therefore you make interfaces only when you need to expose some part of your system to the outside world. And by outside world I mean other systems which use your system. Another thing is that because interfaces are abstract classes, there are no actual instances of objects of these interfaces. And in some programming language, more modern Java versions, there may be so-called default implementations of interfaces. But in general, what it means is that the interface is just abstraction of different, more concrete objects. And you still need to know what kind of this object is and how, especially if you need to create one. If you already have reference to this object, you just can say fly and that object will fly somehow. But if you need to create such kind of object by yourself, you still need to know what kind of classes are implementing this interface, or in more abstract terms, that means what are concrete classes which allows you to create instances from this interface. And here again, it can be tricky if you do not understand these interfaces properly. And typical pattern for different kind of interfaces is so-called factory method, that you can create a concrete object by saying like get this kind of object for me, etc. Now a little bit about more concrete patterns. There are many different design patterns of your software. And if you are into simulation or into handling real hardware, because difference between management of real systems and simulation is not so much. Because if simulation is quite precise, then game is not different from real life. And then, if you need to deal either with hardware or with simulation of different processes, then you may need different kind of patterns for algorithms. How exactly to simulate what numerical methods you should use in this case, what is most efficient algorithm for this and that, etc. So if you are curious about this, there are big pile of books written by Donald Knuth, and it's called Art of Computer Programming. And that part of programming is actually about algorithms. And algorithms are the closest ones to mathematics or mathematical theory. So it deals with number of operations needed for specific number of elements, because usually you need to handle with many things together, not just one single thing, etc. But this course is not about this part, because we are talking about overall design of systems. So if you are interested about these algorithms, then that's different course. Then, particularly for hardware, there are different kind of design patterns, how exactly computations can be made. It's about designs for central processing units, for random access memory, maybe for hard disks and SSD disks, etc. So that's about transistors and logical gates and other things. Again, because in Latvia we are not working very extensively in hardware manufacturing, and we are just using already designed and implemented chips and chipsets from other manufacturers. We will not talk about these things. But then there are these different kind of patterns which are about algorithms to handle entities, to handle different kind of data types and data structures, etc. And I will talk about these ones because these are probably most relevant also for your practical exercise. First, it's about execution, about what are good ways to execute different kind of parts of system to get best benefits. Then about implementation, how to implement different kind of common data structures and behavior, and how to structure your system in structured and more better way. And why design patterns are used? First, because previous history and experience shows that there are some reoccurring approaches how to deal with different but similar things, and it makes software design process faster. For example, if you are a chess player or Go player, then knowing these simple rules about strategy and general behavior, it makes life much easier for you, because these are like basic building blocks how you deal with more complicated problems. So it allows you to reuse more of code. It also shows best practices, because if it's established pattern, and you know it and everybody knows it, then you can't implement it completely incorrectly. Also, these patterns may be like common vocabulary or dictionary to talk between different involved parties. Usually it's not about, it's about peer parties, like you need to integrate software and you talk with other designers and programmers from other companies. And in general, it allows you to create better solution because if smaller parts of system are built correctly, then probability that entire system will be put together more or less correctly, of course, is bigger. And when you deal with different kind of data structures, one thing what you need to do is to create new entities, or in object-oriented terms, entities more about relational databases. But because entity in general means only structured data, but in object-oriented term, object means structured data plus its behavior and related methods. So you need to create these objects and somehow deal with them. And you can create them in different ways. And one of approaches is because of this polymorphism and generalization, specialization, or inheritance is that you may have some more general class, either interface or abstract class, which allows you to create these objects. But when you create them, implementing class actually is more specific and concrete, which allows you to use actual implementation and create specific object out of this more general class. And because of this abstract factory approach, sometimes these methods are even created, named like factory, blah blah blah. But sometimes because of this convention about putting things means set and getting things means get, this may be something like get instance or get object or whatever. And so then you can create subset of little bit different kind of objects using still the same approach. Then you have different objects which sometimes may or may not have different kind of parts. If you just use like factory method, you create everything at once, which is nice, but then internal structure of these objects will be completely the same. But if you have optional parts for these objects, like here for cars, it may have more or less wheels or more or less extras or whatever, you first create completely empty object, not completely empty object, but which has only essential parts, like what I told before, like engine, body and wheels. And maybe not wheels, because different wheels may also be extras. But then you use the setter approach, you set more optional extra parts into this object for that object where these extras are needed. This is called the builder pattern. So this object here can be completely empty, no any data structures inside it. Only thing this object will know about it is that it is instance or object in jargon of car builder class. But then you add all needed internal structures step by step. And if some of these are not needed for this particular object, then of course you do not add these parts. So builder approach is building object not in one large single step, but building it like building in conveyor line. More and more things may be added later. And then you return reference to this built object. Another creation of object is very important is lazy initialization, because any large system, problem with large systems are that they start very slowly. It may take many seconds, many minutes, or whatever. And to make these things a little bit faster, for example, modern text editors are very huge and complicated applications running hopefully on your computer, not somewhere in the cloud. And in most of cases, you don't need 90% of their internal complexity because you don't use these features. So what do? They do not initialize, and that means also do not load into memory unneeded parts of these huge programs. And if everything runs in single thread, you can just do something like this. So if this particular object is needed and this object is not created yet, then create it. And here another pattern may be like a factory pattern or builder pattern if you need it to build it in a little bit different way. And then you return. What is wrong about such lazy initialization? That if your program will run in concurrent threads or processes, you may create more than one such object, and in many cases you don't need many objects. And then singleton pattern comes in. What is singleton? This means that you never create more than one single object inside your application. And singletons are different kind of container objects inside your application. For example, everything inside your text editor, your programming development environment, in graphical editor, music editor, or whatever, there are many things where you don't need to have more than one container. And then inside this container may be many things like many tracks, many paragraphs, or whatever. And to be sure that you do not create more than one, you need to add, particularly for like Java programming language, synchronized keyword that every time when this object is actually created, creation of this object is always executed in sequence, so not in concurrent and in parallel way. And that's about different. And again, I'm just mentioning the most prominent ones that I have seen in my programmer's life, but there are more different kind of creation and patterns as well. Then there are structural patterns, or how you deal with data structures. And one important thing is that anytime you need to iron out some small differences, you need to add adapter or stub. But the general term for this is adapter. You adapt to small differences. And in real life, adapters are like getting adapter from UK to European standard, from European standard to USA standard. Everywhere where you get accelerated current or electricity, it is accelerated current with either 120 or 230 volts and either 50 or 60 hertz. But there are differences in sockets, there are differences in plugs. So to adapt them, you need to add something in between. And similarly for programming languages, if you got some data structure for object like customer, and its internal properties are a little bit different, like date is real date in one customer object, but date is like string, or as I showed you earlier, internal structure of just integers, like integer numbers, you need to adapt for these small differences. Meaning is the same, but actual implementation and technical details are different. So you introduce these adapters and you create in a such way that every time you need to do something for this client, which calls like method A, which means like get electricity for me, through this adapter, through other object method B is actually called like get electricity in this way. And in jargon, adapters are also called wrappers. You wrap original implementation or interface in your wrapped class. Another thing is composite, which allows you to create tree-like structures. And for tree-like structure, you usually have one particular component. For example, typical tree-like structure is file system for your computer. It may consist of files and folders, and inside folders may be files and folders, but there are no anything inside files except their content. So then this composite pattern reappears that you make generalization or abstract class called component. In this case, that would be like in Java it is called file. In Java, file may be either actual folder or file with different properties, but here it's called component, and if it is final element it's called leaf. So, and if it's still not final element like folder, it may have references or contain other parts. And remember here, when you look on internal parts here, there is not infinite loop here, because here is class diagram which represents many instances or objects in jargon, and that means that there may be some composite structure which may have more child structures from this abstract class, and because it's abstract class, actually these will be either leaf elements or other composite elements. So anytime you need to deal with tree-like structures, and it may be also mesh-like structure, then only difference is that here you do not have one parent but many parents. But this is an unusual case. In most of cases you try to deal with trees, because dealing with trees is much easier than dealing with meshes. So remember that this is already solved puzzle how to deal with tree-like structures. Then there are behavioral patterns, or how something behaves, and the most prominent one, at least in my experience, is pattern called iterator. Every time you have some kind of collection, it is very nice that you can iterate through this collection by creating iterator over it. And in this case, this collection may be just a chained link or one-dimensional array, so not tree-like structure, but of course you can create iterator also for mesh and for tree-like structures. And in all modern object-oriented programming language, every time you have a collection of some items, you may create iterator over it and to iterate. And for example, it is either for each loop or for loop or something different, something similar. Then there are strategy patterns, which is about different implementations. So if you have different kind of implementations, as I told earlier, for encryption, decryption algorithms, for security handling, like different authentication methods through Google accounts, through Facebook accounts, through internet banking account, or just a pair of separate username and password or whatever, these are still just authentications. You need to prove that you are this particular user. Then they use a strategy pattern that there are specific way to do authentication. In this case, sample shows execute, and then you have more concrete cases how exactly this happens. But from general perspective, it's just still the same thing. And usually what is needed here to deal with dependencies is some container, very regularly called context. Context is container which stores all related information regarding to current situation. If this is web application, some part of context may be stored on client side, like in cookies, but some part may be also stored on server side. So that is context in abstract terms. So where I'm in this particular application, what I'm doing, who am I, etc. And of course many of these things may be singletons because I don't need more than one particular data structure, etc. Then in more distributed systems, you may need to notify about changes to many objects. For example, you may have many subscribers to some events, and I'm not talking about like subscribers to YouTube news or TikTok or whatever. I'm still talking about one single system running on single computer in single place, but its internal part is in such a way that there are many listeners or observers which want to observe or listen to changes for some particular subject. And then what do? You create so-called subscription service. There is the subjects and observers may subscribe to them, and then you iterate through them, again different pattern about iterator, and you send all these observers about some changes, what has happened in this particular case. What is important here is that with such subscription model or observer pattern, you don't have busy waiting. You notify these observers only when you have something new to notify. And then I will also touch a little bit about other patterns just by names. And for large complicated systems, very important patterns are about concurrency. That means execution goes in concurrent parallel streams, and problem is that these streams are not absolutely independent. If they are absolutely independent, that's very easy, but when you need to synchronize some kind of work progress between this parallel execution, that is the biggest headache for you. And therefore, particularly for these concurrency patterns, which are very important for large complicated systems like for Google, Amazon, and Apple and whatever, or Facebook, there is a completely different subset of problems because of concurrency things. For example, how you handle so-called transactions, that many users working in parallel do not lose or do not create money out of nothing or any other business entities or objects, how to monitor changes, how to deal with other things, etc. But because this probably is not very important at your current stage for your practical work, I will just mention them, because if you will go into this particular area of business, then you need to remember that parallel execution is cause for many different challenges in system design. And then about weaknesses of patterns. In general, you should learn and know at least the most widely occurring patterns in programming languages, because that's like a standard set of moves in particular game, like chess or checkers or whatever. So if you don't know them, then your life is much harder, even in simple cases and simple scenarios. Patterns always have several classes when you look on them in class diagram when you describe them, etc. So there is no pattern just for single class. And because if you have very few classes which are very independent each of other, you may not have any regular pattern inside it because you do not have this standard set of relations between objects of these classes. How do they interact? Other thing is that there are different programming languages which are more or less powerful and expressive. What I mean by power and expressiveness, I mean that you need to write less to say or tell or do more. And particularly Java, as a programming language I little bit know about, Java is very verbose programming language. It becomes better and better if you work with most modern Java versions like 11, 12, 13, 15, 19. And Java is quite popular with patterns because Java is verbose and simple programming language in terms of expressiveness. And there are programming languages which are more powerful, say they do not have such patterns because there can be just one single, more complicated object already be used in this particular programming language. So you don't need to create this pattern of 3-4 different classes. Another thing is that you don't need to seek for standard patterns in any simple particular case, because in simple cases there may be cases that there are no any even standard patterns inside them. And if you will introduce these patterns, you may create the design of your system more complicated than it needs to be. And then I will not talk about this in details, but there is also patterns which are actually anti-patterns. And what are these ones? These ones are patterns in software design which are regularly reoccurring, so that means they are quite popular in terms of their appearance in design, but which are actually anti-patterns. And typical anti-pattern is duplicated code. Because of these small differences between specific instances of a class, you do not create generalization specialization, but you create almost duplicates of code, almost duplicate of your design, only because of these small differences. And then there may be other different kind of patterns which you also should look at if you are curious, because these are different kind of designs in software which are popular, but this is bad popularity, so it happens because of bad design. And with that I have finished this first part of today's session. Do you have any questions or comments? And second part of today's session is about more complicated things or distributed systems architectures or architectures of distributed systems. In previous topic I told you what are recurring patterns or these design structures for single standalone system. And here I will try to introduce you to architecture of distributed systems, which has several parts, and these several parts may be different, like multiprocessor architectures, client-server architectures, distributed object, blah blah blah. Again, I will not touch multiprocessor architectures because that's architecture about hardware, and we don't have much of projects going on somewhere in Latvia, also for international companies working in this area. But when we think about software, about handling data in distributed systems, then these architectures about client-server, distributed, peer-to-peer, service-oriented architectures may reoccurring quite often. First, what is distributed system? One single system still may be complicated but not distributed if interaction between its parts is inside the same, framework, is the same standardized interfaces. For example, if you create complicated system but you still use the same programming language, the same frameworks, the same development environment, then it is modularized, large, complicated, but still single system, because everything is from framework perspective, language perspective, approach perspective is still the same. And if it's deployed on the same server, it's still single system. There may be large systems which are distributed for scalability reasons. For example, any large IT company like Google, Facebook, Apple, Microsoft, they have centralized systems which are a little bit decentralized for performance reasons, etc. But distributed systems are such systems which are split into parts in more separated way. For example, they interact by just sending data from one place to another, but they may be programmed in different languages, they may be living on different servers, they may be implemented using different frameworks, etc. So, and all these systems which are complicated enough are distributed systems, and only question is how exactly this distribution happens, and if this distribution happens in terms of distributed hardware for load balancing and failover, etc. We still think that this is one single system where distribution happens on lower levels of its dependencies. And because any complicated system tends to become distributed sooner or later, of course you need to know something about distributed systems and what are main challenges, how to deal with them. And systems may be different when personal computers, now mobile phones and tablets, become popular. One of most widely used system was system for personal use. And systems for personal use are not distributed systems because everything runs in the same physical computer, in the same operating system, in the same frameworks, etc. But when these standalone single users start interact, then of course they may create a distributed system out of these many standalone systems. Also, most of different kind of embedded systems, that is system or software coming together with hardware, is standalone, not distributed system, because even though it sends data, for example, different kind of network switches, network routers, elevators and lawn mowers and vacuum cleaners like Roomba, etc. They are also standalone systems, not distributed, because system itself is independent, even though they may send some data to Big Brother. But the distributed systems are these which many differently created, designed, maintained systems work together. And typical example, actually bright example, is Internet. Internet is very bright distributed system because very many different devices somehow work together, and you shouldn't claim incorrectly that Internet is biggest single machine in the world, because it isn't. Internet consists of many small distributed separated machines somehow put together, and everything which is closer to Internet than to your Roomba vacuum cleaner or lawn mower or router, it is distributed system, and if it's closer to router and personal computer, then it's probably single system. And why distributed systems are used? First and most important thing is to share resources, mostly share information, share data. So information is structured data which shows you some insights. And that of course is big part of computers and software to share different kind of resources together. Then other things which are important in some cases are concurrency or execution, concurrent execution for performance reasons, and scalability, again, because if you have very large mega system, it cannot run on single poor hardware as far as anyway how powerful it can be. It may not be enough, so you need to create a distributed system putting many computers or physical hardware together to provide services for probably a single large system, but it's distributed as a, how to say, dependent parts for it. And sometimes you also need to be more open to share these resources and data with other things. And what are disadvantages? First, any distributed system is much more complicated than any single system. And you do not create distributed systems without important reason. And most important reason is sharing data. Also, security becomes much more complicated. Maintainability, manageability, predictability becomes much more complicated because there are much more moving parts, and if these moving parts can move concurrently in parallel, then you may have different kind of runtime effects which you cannot see through debugging, through compilation, through testing process. So you don't use such complexity of distributed systems without serious reason. And what are main architectures? The most leading architecture is client-server architecture. That means one single hub of something called server, and then many clients around this server which are using these services provided by server. And other approach is more widely used as a backend system for business automation and for standardized things like financing, like banking, etc. They are separated systems, but so you can't say here is one single server servicing something, but there is distributed architecture, and objects are sent through from one place to another, from different servers to servers, from servers to clients, etc. And middleware is a specific software which is used as a glue or intermediate layer between different systems which are very different in terms of the technical things like programming languages, dependencies like operating systems, etc., but which work in similar business domain. Like they are very different systems to deal with financing, money transfer and logistics and other things. And in such systems where business is common but implementations are very different, usually they have some kind of software which allows to iron out these differences. If you would look on one single case scenario, that would be just adapter pattern, but because one adapter is not enough to glue together complicated systems for financing, etc., you actually have entire software dedicated for ironing out these differences between systems. And so middleware is software which serves other software. It doesn't serve real people, doesn't serve humans, but it serves other software. So in simplistic terms, it's like a software library. It is not used by humans, but it's used by other software. And so one is about financing, another thing is about communication controllers, like for networking devices, for Internet of Things devices, for monitoring and maintaining manufacturing processes in factories, etc. So there are short kind of software which allows you to use middleware. So if we look on simplest example of a distributed system, one of simplest examples is modern central processing units. In general, because of physical limits, there is no good reason to run single processor faster than with frequency of few gigahertz. If you want to make a system faster, you can put in the same single chip more than one processor. Good thing about such distributed systems is that they are all equal in terms of their behavior, complexity, etc. So it's easily scalable. You just put many copies of the same system on the single chip, on the single hardware, and that's easy way how to scale things up. And such multiprocessor traffic control systems may be used also to manage real-life systems where latency is important. Latency is time which is needed for some reaction. For example, if you do ping command in command line, it checks latency of your data transmission networks. For example, something in internet or local area network like Wi-Fi or Ethernet. And if you need to do something in real time and your latency is important that it doesn't take more than a few milliseconds and you have many things to control, you just add more and more processing power. Each of particular processor processes some part of entire system and you scale things up. And such scalability is quite simple because usually for this monitoring there are no need for shared information. There is no dependencies between these. These are completely independent, and scaling up completely independent systems is quite easy. You just add more parallel concurrent resources to deal with them. But when you need to deal with shared resources and dependencies, then it is much harder. And simplest one for distributed systems to share information is client-server architecture. This means one particular instance of software runs on some hardware is like a center hub of information, like a single point of truth for all your information, and then this server is accessed by many clients. And in client-server system, usually they represent like tree-like structure, because one single server serves many clients, but one single client usually connects only to one single server. And then when you have clients communicating to server, there is important political decision where you draw border between client and server. And in simple cases it is quite easy to understand, but in more tricky cases there may be some parts put either on client side or on server side. Each of them have their own benefits and drawbacks. And usually on server side you implement system architecture which is called layered architecture. Layered architecture means that there are actually servers serving servers. For example, you may have a relational database management server servicing particular business application, like for counting money, serving customers, or serving issues, or dealing with warehouse management system, etc., etc. And then there is presentation layer, which is actually shown to real users what they see on screen. And this is well established architecture, because every time you have complicated systems, you do divide and conquer approach, like Julius Caesarus did when he established Roman Empire. So, and you divide and conquer in such ways that if you have relational database management system, it will serve you well to deal with relations between different kind of entities, like customers and orders and items and shelves and warehouse, etc., etc. And you can delegate all these actual implementation, how to serve these relations well inside this server. And then your application server actually is dealing only with specific kind of business. And presentation layer deals only with either graphical interface or web interface or whatever. And this is typical 3-layer architecture. When I told you about other, you can also see this MVC pattern here, because this is your model, this is your controller, and this is your view. And then political question appears here. Where do you put handling of business logic? And in local area networks, before internet was widely used, usually on server side was only relational database management system like FoxPro or DB2 or Cbase or Microsoft SQL or whatever, and you installed client like Horizon account system where business logic was built inside client, so as many clients you had, as many separated entities, instance of this software you had, and they sent only requests and got a response back to relational database management system. It's still used if you have many clients, single server in local area network. Doesn't work very well if clients and server are connected through the internet, because then You need to establish secure connection between client and server, encrypt data, etc., etc. And therefore, if this client is, so this is called FAT client. FAT client means business logic is inside client, and here actual raw data are transmitted through the network. But thin client model is like a web client, and you have web application server. Then business logic is on server side, and here instead you don't need to install anything, but here your client talks with server using HTTP protocol, HTTPS and HTML, JavaScript, blah blah blah. And neither is ideal. Good thing about FAT client is that it is easier to scale up, because all complexity and computation power is actually happening on client side, so server is less busy. Bad thing is that it is FAT and you need to install it. And of course, most of Android applications are also FAT client applications, but many of them are actually thin client applications which just hides that they are actually like web applications with too much of JavaScript inside them. So that's about these layers and thin and FAT client. So typical web application is thin client because business logic is on server side, but particularly for mobile applications this division is quite blurry. So then about layers, even though we talked about 3 layers like till to relational database, of course there are more than 3 layers, because relational database server actually relies on service provided by operating system, which relies on service provided by hardware, etc. So actually you have onion of layers of systems using systems using systems, because you take as much services as you can for granted, because every code you do not write yourself, you don't need to test, you don't need to maintain, you don't need to improve. And only problem is that layer on top of layer, sometimes if something goes wrong inside these layers, then of course dealing with such issues is quite complicated. And therefore another political question is how many layers you may have. You may have only 2 layers, like application, client and database server, then this tend to be relational database server, and this tend to be FAT client. If there are 3 layers, this tend to be web client, web server with business logic, relational database. 4 layers may be for more integrated systems for large enterprises. You may have relational database, you may have your middleware with different kind of domain entities for customers, for issues, for clients, for orders, for blah blah blah. Then several applications and user interfaces. And then you may have partitioned them vertically. What means vertically? Horizontally means up closer to the software, more general thing, down closer to the hardware. And if you put these vertical integrations, this means you have particular set for particular business domain, like different kind of business applications. And then when you have many layers, you may have either closed or open architecture. Closed architecture is more secure. This means every layer can talk forward and backward only to the next layer in between these stack of technologies. Good thing is it's more secure, easier to test, to debug. Bad thing is it's much harder to implement new things, because many things are encapsulated. If you need to add something, you need to add something in lower layer, upper layer, etc. because you can't reach it, etc. So good thing you can't abuse it, you can't break it, it's more secure. Bad thing is that when you need to introduce new features and integrate things, it's harder. Open architecture means that you actually may use this layer or that layer depending on what abstraction layer you want. And open architecture is very typical for sound systems, either for Linux-based operating systems, for Windows-based operating systems. I'm not so sure about iOS and macOS because it's quite closed by nature. Because of legacy software, because of backward compatibility, when more abstract, more modern layer is introduced, it usually still allows to reach lower level for some applications which do not want to use this particular layer or interface. So, what is good? Adding something new is easier because you may choose either this or that. And for example, if you are C programmer, open architecture is for different kind of C libraries. You may use some older, closer to hardware libraries if you still want to, maybe much less secure because of buffer underrun, buffer overrun problems and stack overflow problems, whatever. But you may also use more modern layers with small built-in features, but because of backward compatibility and legacy software, it is still allowed. So, more complicated, but also may work. And when you introduce something new, you always need to consider, do you need to support previous approach or not, and then you decide. Or if you use some already open architecture where you can access different kind of layers, you need to think about what is easiest way for you. That's about... Then about distributed object architectures. Client and server is architecture where specific client connects to specific server, so they use common understanding, common protocols, how to exchange this information. But if you have several clients and several servers, sooner or later you end up not with direct relationship between client and server, but you just might send objects through your media, usually local area network or global network like internet, where you send objects. And what is object? Object is structured data, which also may say to which class it belongs and how you can deal with its properties, so what methods you can call, etc. And so these are different kind of distributed object architectures. And one of first standardized international standard for distributed object architecture was standard called CORBA, not COBRA, but CORBA, Common Object Request Broker Architecture. And it was developed by consortium of all large IT companies like SAP, IBM, Oracle, and many. So these large companies which provides business process management systems for large organizations. And later it was also managed by OMG, Object Management Group, which also manages UML standard and BPMN standard. So and they decided and agreed on standard how you can send these objects through the distributed environment in common fashion. And what they introduced? First they introduced that there is service called Object Request Broker, which listens to new events, new requests. And clients do not connect to specific services, but they connect to this broker. And then broker works like a traffic regulator, traffic manager, And if some client requests from this broker this or that, then it connects and executes something and provides data to this client from different places. If you already know something about programming language, there is interface in Java called serializable. If you implement serializable interface, you can send any object through the network or save store in file system easily, and then you retrieve it back and you got object either from network or from file system or whatever. Only problem is that serializable works only in Java environment, so it is Java object, and Corba is standard which allows you to send receive objects through the network similarly for any programming language implementation, either for this client or object request broker or Corba services. So it created standard which says what message structure is, which is platform independent, like what date is, what integer is, what string is, what anything else is, and how these messages are formatted, how these are sent, and how this traffic is regulated. And because such a Corba object request broker might work for entire internet, of course one of built-in features for it is authentication and authorization. This means policy, how you authenticate your clients and how you can prove that you can access this particular service and get this data through this broker. And so there are application objects, standard objects defined by object management group, fundamental Corba services, and horizontal splitting means how you actually implement it in different programming languages. At that time when it was developed, the standard, most programming languages were C, C++, and Java. So they introduced standard which is common denominator for all of these programming languages. And so then there are these listening services which waits for messages, like any server. Only difference is that they are listening for these object requests from Corba clients. Then they do check policy, can client actually access to this service and get this data, and then they do request actual object created by more specific Corba service, which actually creates these data structures or retrieves or creates these data structures for specific systems. So if you call for a particular customer using Corba, then you get particular customer for some system through this Corba request broker. So then they also introduced what are naming and trading services, notification, transaction services, how exactly this communication works, etc. Last time I was interested about Corba by myself was approximately 20 years ago, when we worked with a very large complicated system called IBM Tivoli, which was monitoring system for distributed networks. And so they implemented this Corba protocol. Everything what you got, every data structure, every object you got through the network was not just serialized Java object, it was actually Corba object through this object request broker. But because I have not worked with such large enterprise systems anymore, I do not know what is current state, how popular this Corba standard is. Definitely they are more web-oriented, more HTTP protocol. And by the way, as a transport protocol here, it doesn't use HTTP. It is still just a raw TCP/IP protocol, where actual requests and responses are implemented in this Corba protocol. And then another architecture, what is very important, is peer-to-peer architecture of distributed systems. So there is no like tree-like structure, server somewhere in the middle, many clients around, but every client may be server, every server may be client. So in general, it is just generalization of client-server architecture, where every client may be server and may be client. But this generalization adds much more complexity, because you do not have one single point of truth, which was on server side, and you have problems with dealing with consistent data, with history of data, etc. If these data are very independent, like in social networks, where some lost record is probably not so important, or not some of new notification is not, for example, when you receive money in your account, it is very important to not skip it. But if you just look on news in your news feed for social network system, it is not so important. So when these dependencies between data are not so important, good thing about peer-to-peer architecture, latviski vienranga arhitektūra, is that it's more scalable, more powerful. And the problem is that if you add one more node, which means either client or server or both, to your network, how you establish connection between this newly created node so that it actually knows everything. And therefore, usually there is no completely distributed architectures. They are somewhat decentralized, semi-decentralized, because you still need to do something like finding out other servers, etc. So what you usually have is, and that how early peer-to-peer network for file sharing service worked, etc. There was more or less distributed system for nodes where you can transmit your data, but there were some discovery servers or directories servers which showed how many clients were connected to this network. And similarly is for digital money like Bitcoin, Ethernet, etc. And similarly is, for example, for Skype network. Initially it was created as peer-to-peer network, because you need to remember that fully distributed systems in total are less efficient, more wasteful than client-server systems. And they are more complicated, and because they are only thing how do they work is because even though total efficiency is smaller, because each of added client also fulfills a role of server, total amount of hardware added to such system is bigger and bigger and bigger, so it still scales up. And therefore there have been many systems which started as fully distributed systems, like Skype communication system, like Bitcoin, digital currency system, which tends to become first semi-centralized architecture, and maybe after some time actually as client-server architecture, because it's more efficient way to do things, and it's easier as well. Or it may introduce also some layers inside them, etc. And so biggest problem with fully distributed system is discovery, how some added node discovers already established nodes in network if they do not have at least one small central part about these directory services. And also it doesn't have single point of truth, so you need to spend quite a lot of algorithms and business logic to understand, like for digital currency it is majority of votes. If majority of node thinks that this history of spent money is correct one, then you decide that this history of spent money is correct one. And of course, particularly Bitcoin, where abuse is controlled by proof of work, it is absolutely inefficient if for transmitting money using Visa cards you need few hundred watts to handle. For Bitcoin transaction you need megawatts. So, and then about modern implementation of Corba. So Corba was invented many tens of years ago, but then after that web happened, and web is HTTP protocol on top of TCP/IP, and this means client-server architecture. Server serves HTTP requests, client does HTTP requests, and then it was added with cascaded style sheets, JavaScript, and other things. But for systems integration, one of easy way how to integrate systems is still use HTTP protocol to exchange information in between distributed systems. And what is called service-oriented architecture is actually HTTP-oriented architecture. So, as usual, names are not completely correct because of historical reasons. So, service-oriented architecture is Corba, where HTTP is used as a transport protocol. And how does it work? It works in such a way that every server who wants to provide service provides this service through HTTP protocol. What does it mean? That there is a listening port, of course listening IP address, and there may be requests, GET requests, POST requests, and it returns some data. And if you need to have some discovery service, then of course you have another directory service where you can ask from where I can get reference to customer, from where I can authenticate myself as a valid user, etc., etc. And what are benefits? Benefits are that HTTP has proven to be a very good protocol for systems integration, and it's easy to implement, easy to test, it's platform independent, and it is widely supported by programming languages, frameworks, etc. And then what actually is provided through this service-oriented architecture is that you have small web services where you can get some request and get some data back. What is not so good is that there is no good standardization how you provide structured data. One of leading approaches is JSON format, or XML format. XML format is older school, more verbose, but good thing is that it is very strict. You know what element is, what like class or complicated structure, what attribute is, very precise types for attributes, and very rigid and strict schema for element inside element inside element, or this hierarchy of object inside object. JSON is more compact, but for JSON only data types are like array, map, and primitive types. And what are leading standards for this service-oriented architecture? All of these are HTTP-oriented or web-oriented. SOAP, which is mostly GET requests and stateless requests, so server don't need to remember anything. If client wants to remember anything, it sends additional information using cookies or other standards. Then there is VSDL, Web Service Description Language, and Universal Description Discovery. So this is how you discover these services, this is how you describe them, and this is how you actually implement them through these things. And for example, in your practical task, if you want to integrate with some external services, probability is almost 100% that you will not use Corba, but you use more modern implementation of Corba. That means common object request brokers through the HTTP protocol, or SOAP, WSDL, or UDDI protocols. And then what is important is that as systems become more and more complicated, but you also have more and more code accumulated as legal, free-to-use open source implementations, for any non-trivial application, you do not write applications from scratch, but you use larger and larger building blocks how to create more complicated systems. If 20 years ago your building block was concepts coming from your programming language, then today your building block may be like entire kitchen or entire living room in your house, where this kitchen and living room are already developed components of your entire system. Of course, not all components are equal. If these components are still written in the same programming language in friendly frameworks, then of course your life is much easier. But I have dealt with systems, for example, in service-oriented architecture, particularly for digital signatures and authentication, servers running on Microsoft.NET, C# and on Windows Server, but client is written in Java, running on Linux-based operating system. But as far as a client implements established protocol correctly, you can still integrate these systems together. And that's where standards are important, and where following standards is also very important. So if you follow good standard correctly, then anybody can integrate with you. If not easily, then at least without any showstoppers somewhere in the middle of the project. And many of modern systems are developed in such a component-based way. I will not be surprised if, at least for some of you, even your practical exercise will be like a component-based system, where you will put different already created components under one umbrella for your application to use it in one particular specific way. And then one of these leading approaches for large enterprise systems is the service-oriented software engineering, that these who provide some information, they implement these as a web services. Remember, service-oriented architecture actually means web-oriented architecture. By web I mean HTTP protocol. So for me, web and HTTP is jargon. Web is for users, and HTTP is for those who understand what happens behind the scenes. And then you need to have implement particular service provided. Then you need to register this service in some registry, otherwise your service will not be discovered. And then these clients just send different kind of requests to service discoveries, then to these services to get different kind of data. And one of these services may be authentication. So problem is, how do you do authentication in distributed systems? You exchange signed data. For example, you may go to some authentication service like DatZ2186. DatZ2186, of course, if you open it through HTTPS, has graphical interface for human users, but it also provides web services for other software. And if you create a software request to these services provided by DatZ2186, then they might refer you to other services like internet bank, etc. And what do? They create a request and then get a response which is digitally signed, which says here, in this case, if you go through Latvija.lv and then authenticate through the Swedbank internet bank, then first Swedbank internet bank says this is DatZ2186, blah blah blah, and sign digitally this data, this token, in this case it's called. And then it provides this token to Latvija.lv, and Latvija.lv checks it and then creates another token or data which says, yes, we check it through Swedbank, blah blah blah, that this is actually user DatZ2186 and digital signature is here. So, and then you send this data to service provider, which checks, okay, looks like it's DatZ2186 because these data are digitally signed and signature matches control, so it allows you to do some request here and it returns you some data. So then, therefore, if you go into more details about distributed system, understanding about digital signatures and dealing with authentication issues also is quite important thing. And then your application actually may be mesh of service requests to different kind of services. For example, digital maps quite frequently work in a such way that there is only enumerated content amount of publicly available maps like Google Map, OpenStreetMap, and few more. Of course, each of states, countries have their own maps usually. And then you can create requests to get this data back, either anonymously or with authentication, to show something, to change something inside this data. And of course, particularly for maps, again, you have this layered architecture. You may have layer on top of layer on top of layer, which you can actually see on your user interface. So, particularly for maps, you can see this layered architecture, how it actually looks on screen. And so, such service-oriented systems architecture is quite popular today because many of particular business systems is actually so-called orchestration or management between invoking different kind of web services. So, what are key points? Key points are following: that distributed systems are needed to share resources, and the easiest way how to share resources is client-server architecture, when you have one server and many clients. Political decision is how fat or thin you create your client. Do you put business logic on server side or client side? If it is on client side, there may be just two-layer architecture. Server holds data, structured data, like a relational database, and business logic is on client, or maybe three-layered architecture with web client or mobile client, and business logic is still somewhere on the server. Then of course you need this server somewhere to live. You need to host some physical virtual instance for it to run. Then old school standard to exchange only structured data or objects is called CORBA. I don't know how widely it's used for SAP or Oracle systems, which are also very large enterprise systems. But more modern implementation of ideas of CORBA is web interfaces. So you provide your structured data through web services, and then web clients written in your particular programming language connects to this service and gets this data. What is not so good is that CORBA defines structure of data very precisely. For web services, there is no established de facto standard how exactly you represent your structured data, maybe XML, maybe JSON, maybe serialized Java objects or serialized whatever objects. So it is less standardized, unfortunately, because for service-oriented architecture, SOAP and REST and other protocols, it mostly talks about authentication, about request responses, not about particular structure of data. And then next big step in complexity is, instead of client-server architecture, to make distributed architecture, which will be much more complicated to develop, to debug, to test, to maintain. Only good thing is that it is very easily to scale up, because each node added can do some share of total amount of work. Remember, it is very bright example. Bitcoin is distributed system which slowly becomes more centralized system. Like any system, if it lives long enough, any distributed system, any peer-to-peer system, if it lives long enough, gradually becomes client-server system, because it's more efficient in long term. And so you do not create distributed systems without good reason, because otherwise you add complexity without any serious